In this lecture, let us look at how we can derive the ideal opamp rules from the practical opamp model. So you remember we had an input resistance represented by Ri and a voltage controlled voltage source here that depends on the open loop gain and an output resistance Ro. So this is how VO is connected in the practical op-amp model, and the input VD is basically the difference of the non-inverting input voltage and the inverting input voltage. So VD is actually equal to V plus minus V minus. That is why it is sometimes called the differential input voltage. Because it is a difference of two voltages. Now let us see how we can derive the ideal op-amp rules from this circuit. I hope you remember the ideal op-amp rules that no current goes into the op-amp. So let us say the input current here is IN or capital IN maybe. The book uses small, but let me resort to using the capital letters. So IN is 0, is the ideal op-amp characteristics, and then we know that VD is 0. So if VD is 0, that would imply that V plus is equal to V minus. Now here in this circuit we can see that if there is no feedback resistor, or there is no feedback from the output to the inverting input, or the case that we can refer to as the open circuit output voltage or open circuit configuration, then the open circuit output voltage VO would be equal to, so there is nothing that connects the output to the input. So whatever is VD will get to the output, and nothing is connected here as well. So VO would be equal to AVD, or VD would be equal to VO over A. Now in practical op-amps, for example, a typical op-amp, the mu A741, Ri, the input resistance, is typically of the order of 2 mega ohms. A, the open loop gain, is 2 into 10 to the power 5 volts per volts, because that's the ratio of two voltages, and Ro is 75 ohms, the output resistance. So here, if we can use over typical configurations, then we know that the output voltage, as I might have mentioned somewhere earlier, but let me put it categorically here, that the output of the op-amp V0 cannot go beyond the two supply voltages that we use. So minus VCC and plus VCC, they limit the output voltage. Remember, an ideal op-amp, whenever we have tried to solve the circuits, I mentioned about this. So an op-amp, say this inverting configuration, this VO cannot go beyond whatever the supply voltage is here, say plus 12 volts and say minus 10 volts. Then VO in this configuration, whatever Ri and Rf is, VO must be between minus 10 volts and plus 12 volts. This is a limitation of the op-amp. Whenever there is such Vi that VO is within this range, we say the op-amp is in linear region. And whenever VO is outside this range, either it is greater than 12 volt or VO is less than minus 10 volts, we say the op amp is saturated. So this is an important thing to know. And when is an op amp saturated? Whenever you compute the output of the op amp and your computation shows that the output value is outside this range, then you will know automatically that the op amp is saturated. And why it is important to know this? Because when an op amp is saturated, the ideal op amp characteristics do not apply. So for example, if your calculation finds for this circuit that VO is equal to 25 volts, it cannot go to 25 volt. And if you test this in this configuration, that configuration in a lab, VO would be 12 volt actually, or very close to 12 volt. Suppose Ri, here we know VO is equal to minus RF over Ri into Vi. So suppose Vi is given as 1 volt and we have a variable resistor here RF, and Ri is say 1 kilo ohm and Vi is 1 volt. RF is a variable resistor that can vary between 0 and say 20 kilo ohms. Then we can see when RF is 0, VO would be 0. 0 and 0 short circuited, VO would be 0. So VO basically varies. For RF 0, VO would be 0, but for RF 20, VO would be minus 20. Actually, we should have written this way. It would be between 0 and minus 20 volts. But we know that the output cannot go beyond minus 10 volts. So for all the values of RF from 10 kilo ohm to 20 kilo ohm, the output would be saturated at minus 10 volts. So actually, in actuality, VO would vary between these two voltages. This is what you will observe, what is reality, and this is what your model says. So the model may say something that is not true in practical life, and this is why we should know the limitations of a model as well. So this is just a recap, and this important bit being taught, that the op amp must not be saturated when it is being operated, or it must be in the linear region. When it is saturated, these characteristics no longer apply, and this is very important. When an op amp is saturated, there may be current going into the op amp. Ideal op amp characteristics do not apply. Op amp ceases to behave like an op amp that we know. It becomes something else that we don't know yet. So this must be very clear. So when an op amp is not saturated, for a typical op amp, for example this MU0741, where we know that the supply voltages can be applied up to say from 5 to 24 volts. So if we need to find the max value that this VD can have in a MU741 op amp, the practical op amp, then the largest value VO can get is 24 volts, and the A, as told by the manufacturer, is 2 into 10 raised to power 5. Then this comes out to be something like say 120 microvolt. So VD is 120 microvolt. Now compare this 120 microvolt with 24 volts. So this is almost as good as 0. So it is really not something absurd that in an ideal op amp we consider this VD to be 0. In reality, even this VD is very small. So we have in a way proven the second ideal op amp rule. Now what about the first ideal op-amp rule? The first ideal op-amp rule can be that there is no input current going in here. Can be seen that I in is equal to Vd over Ri. Now for mu A741, Vd we know is 24 volts and Ri is of the order of 2 mega ohm, 2 into 10 raised power 6. This would become something like 60 pico ampere. This is very extremely small current, and as compared to the currents that would be flowing in the circuit, for example for here and here, the 60 pico ampere is as good as zero. So we have derived the ideal op-amp rule 1 here and the rule 2 here. So we have just seen that Ri is a very large value in an ideal op-amp, can be considered as infinity. A is a large value, can be considered as infinity. Ro is a small value. This Ro is actually not considered here right now. So for an Ro, just look at this VO. So VO, if there is some IO flowing, we can see that VO would be equal to A Vd minus IO Ro. So there would be some drop here because of this IO, and this drop is going to reduce the output voltage for varying currents, and we don't want this in our ideal op-amp model. Therefore we consider that Ro is 0. So Ro is a small value, we consider it as 0, and VCC are the supply voltages. VO never goes beyond this. This is very important to know that VO must be between the negative of the voltage we use, and then we know there are two voltage sources. One is the negative and the other one is the positive. Different books can have different nomenclature for or labels for these, but I have tried to use VCC for them. They can be the same, they can be different.